Okay, today we're going to go over water and then make our way all the way through pH and acids and bases. And basically, they all kind of blurred together, so we're going to go over them quickly, but then again, like I have said in almost every video, cement them in the classroom, the ideas that we're going to look at. So, like we learned yesterday, we learned that the water molecules are very polar, and that polarity actually helps them to be such a good solvent. They're able to kind of separate some of the things in our bodies, like sodium chloride, into little individual ions so that our body can use them. So we have already learned that water has that negative part from the oxygen and the slightly positive charge or part of the molecule thanks to the hydrogens on the end. And we're going to learn about how they like to arrange themselves in, let's say, like a cup of water. So the first vocabulary word we're going to learn is hydrogen bonding. So whenever we look at a cup of water, and we're going to look at a few examples in the classroom, but if we were to drop some water on the floor, they wouldn't every molecule go its own way like a bag of Skittles, right? They kind of puddle together, and that's called hydrogen bonding, or it's due to hydrogen bonding. And that's because this negative part on the oxygen is almost like a tiny little bond. It's very attracted to that positive part on the hydrogen. So the hydrogen bond is when that negative part of one molecule, water molecule, is attracted to the positive part of the other molecule. All right, so you may or may not have heard about cohesion and adhesion in your middle school classes. But basically, cohesion is the attraction between molecules of the same substance. So, for example, water molecule being attracted to itself. For example, like this picture. The positive part of the hydrogen is attracted to the negative part, the oxygen in the water. Adhesion is when it's attracted to different substances. And again, we're going to look at an example of that in class. But it's basically when, for example, water is attracted to glass and you get that meniscus in your graduated cylinder. And if you don't know what that is, don't worry, you will by the next class. So we're going to talk about next the solutions and suspensions. So what that is we're going to be looking at things in the lab, and sometimes it's going to look all the same, homogeneous. Homo means same, homogeneous. So we're going to look at something that looks the same, but it's not the same. If we had a little tiny crane that pulled out a molecule, one molecule at a time, they won't be the same molecules. There's water in here, there's fat, there's sugar, there's protein, there's a lot of stuff inside the milk, but it just looks the same. So it's a homogeneous mixture. It's a mixture because every atom isn't, or every compound or atom isn't the same, but it's homogeneous because it looks the same throughout. Heterogeneous, on the other hand, it's still a mixture. It's more than one different type of compound, but you can see the different phases or parts. So, for example, you can see the different types of nuts. You can see pecans and pistachios, and I don't know what else is in this thing. And then oil and water, they don't mix, so you can see the different phases. So heterogeneous mixture, so both of these are mixtures, right? They're not the same compounds together. This one is a mixture, but it's heterogeneous because we can see the different phases. You can see the oil here and then the water. Homogeneous means same, so it looks all the same throughout, but it's still a mixture because it's not the exact same molecule over and over again. Okay, so we're going to take a look at homogeneous mixture on this slide. So remember, a homogeneous mixture is something that is the same, it looks the same throughout, but it's not the same in size. So there could be multiple different molecules within it. So there are two parts to it. There's the solute and solvent. Solvent is the one that's doing the dissolving, and the solute would be whatever we put in there. So a good example is if we were to put salt in water, the salt would be dissolved, so that's dissolved, it's the solute, and the water would be the solvent, it's doing the dissolving. All right, and then suspensions. So we're going to look at suspensions. This is, you can look at it as like a yogurt. A yogurt is like proteins suspended. Our blood cells are actually cells suspended in plasma. Okay, so they're not dissolved. So for example, the blood cells are not like dissolved apart inside the plasma. They stay their little blood cell self. So that's a suspension. It's basically something that just kind of sits in the water like a precipitate type thing. Okay. Okay, so something really cool about water. So it's like the reason there's life on Earth. It's you have to have water for something like us to be on a planet. That's why NASA always is looking for water on other planets because if you have water, then you might possibly have something like us on that planet. So, some of the properties of water, especially the most important as far as maintaining temperature on Earth, is that water is able to absorb and release water. So, our Earth gets really hot and really cold, but water is able to absorb that heat and release it when it gets a little cooler. Okay, so that's what this is paragraph is talking about. Temperature regulation on our planet. That's like super important for us. Okay, so you will hear that water is the universal solvent of life. Okay, so it's able to dissolve a lot of stuff. And our body is made up of, it's about 70% of water, depending on your size, weight, whatever. But basically, it's a big chunk of our body. And the reason it's so important is we'll eat something, but we need to be able to dissolve it into tiny, tiny pieces, molecules. So water, because it's so polar, it's able to split open because of its positive and negative part of the molecule. It's able to split open and separate things like sodium and chloride, which is an ionic bond. It's able to open those ionic bonds in order for us to use the different elements within it. All right, now we are on to acids, bases, and pH. So again, we'll see all of this in class, but this is just a quick introduction. But you probably have seen the pH scale before. We usually like to stay at around a neutral 7. We're slightly more basic than neutral, but we typically stay around 7. And then the lower the pH number, the more acidic something is, and the higher the number, the more alkaline or basic it is, okay? So usually if you touch a base, they're usually really slimy. So things like seawater is not quite slimy, but it's more slimy than regular water. And soap is slimy. If you've ever felt bleach, I've got bleach on my hands before. It's just anything that's alkaline typically has this slimy feel, and that slime helps for bacteria to slip off of our hands. So that's why we usually use those as soaps. Now, if we're wanting to actually kill bacteria, so for example, alkaline stuff kind of helps the bacteria slip off of our hands, and that's why it's good to get a good lather when you're washing your hands. But if you're wanting to like pop the bacteria or just like kill them instantly, we usually use something acidic, okay? So yeah, that's kind of just a very brief introduction of acids and bases. The pH scale runs from 0 to 14. We're not doing any calculations with pH, I don't think. So we're just going to talk about, what it does within something living and why it's important. So the definition of an acid that we're going to talk about is something that will donate a hydrogen ion. Okay, there are 3 different, if not 4 different definitions of acids, but in this class we're just going to talk about the fact that acids will donate a hydrogen ion. There are more complex acids, but we're not really going to deal with them in this class. And an acid is a pH of lower than 7. Okay, so for example, our stomach acid, tomato juice, carbonated drinks, vinegar, all of that has acid in it. The bases are compounds that donate hydroxide ions. The OH minus, that's called hydroxide ion. Okay, so that's the definition we're going to stick with in this class, even though, again, there are 3 or 4 different definitions for this. Some examples are ammonia, soaps, bleach, sodium bicarbonate, that's just baking soda that your mama uses to bake you a cake or something on your birthday. So, yeah, they usually have a pH of higher than 7. Now, buffers might be new to you, they might not, but a buffer is basically something that tries to keep a pH a certain pH. So in our own body, we make our own buffers so that our body can fluctuate a little bit without being deadly. So we have some buffers inside of our body so that our pH doesn't get too high or too low, because our body isn't always intaking the exact same thing every hour of the day, right? Sometimes we eat acidic food, sometimes we eat basic food, sometimes if we get an infection, our bodies can be a little more acidic. So we have these buffers to help keep us alive and to keep that pH from getting too high or too low. Just like we have insulin that helps our sugar stay at a certain level, a buffer helps our pH stay at a certain level. It's all there to help us maintain our homeostasis, which everyone knows that.